Now, the forces here were obvious. And yes, he survived. That was kind of fun. So guess what? Those forces have to get transmitted in some way. Now we're going to go look at what are known as the elementary particles, the things that make up matter, the things that make up forces. Okay? Maybe you've heard of things called quarks and leptons. Notice in my peak box there, down at the bottom, it says atoms and molecules. We studied that from chapter 1 or module 1. We've been looking at those. But guess what? Those are made up of smaller particles that break down into what are known as quarks and leptons. That's what makes up matter. But the forces that we talked about, there's 4 fundamental forces in the universes. There's the strong nuclear, the weak nuclear, the electromagnetic, and the gravitational force. Each of those forces have what's known as a carrier. So let me introduce you to what's known as the Standard Model. I like to think of it as God's Legos. Okay, those quarks and leptons in the Standard Model, that's the greens and the purples. The forces, the force carriers, those are the things in blue. Notice we've got that Y-looking thing at the top of the list. That's actually the Greek letter gamma for photon. Then you have the letter G for gluons. Okay? And then we have what are known as the W and Z bosons that are associated with the weak nuclear force. And there's one more here, the big G, the graviton. Particle, the force carrier for gravity. Alrighty, let me take you a tour on these 4 fundamental forces. From strongest to weakest, we have the strong nuclear force. Then we have the electromagnetic force. Then we have the weak nuclear force. And then we have gravity. But let me help you understand just how strong these forces are relative to one another. The strong nuclear force is the strongest force in the universe. So we'll give it a relative strength of 1. Let's say its value is 1. The electromagnetic force, which is the second strongest, is 100 times weaker. Only 1/100th as strong. The weak nuclear force, which is the third strongest, look at that column way to the right where it says relative strength, 10 to the minus 13. It's 11 times weaker than the electromagnetic force. And then finally, gravity. Yes, gravity is the weakest of the 4 fundamental forces. Look at that number, 10 to the minus 39. Now, if you're like me, I can, from a math standpoint, I can understand, yeah, that's a whole lot smaller than number 1 for strong. But I said, there's got to be a way to kind of visually get an idea for how these things compare. So I said, let's start it the other way. Let's make the strength of gravity represented by a single grain of sand, about 0.5 millimeter in diameter. So one little grain of sand represents how strong gravity is. The next strongest force, the weak nuclear force, would be represented by a ball of sand that would reach from San Antonio to Austin, Texas. That's a big jump in the size of your ball of sand. The next strongest force is the electromagnetic force. Guess what? It's a ball of sand almost as big as the sun. Almost. So gravity is a single grain of sand. The weak nuclear is a ball of sand that reaches from San Antonio to Austin, Texas. The electromagnetic force is a ball of sand almost as big as the sun, and the strong nuclear force would be represented by a ball of sand 3.5 times the size of the sun. Hopefully that gives you a better feel for how big the range of the strength of these forces are. But remember I said these forces get transmitted? Well, there's some ugly equations on the right-hand side that explains how the force of magnetism can be calculated. But what it boils down to is there's actually an exchange of photons between matter particles that create the magnetic force. And similarly, got this lovely equation in the middle of the page, Fe K Q1 Q2 over R squared. Tells us how strong the electrical force is. But what's doing it is an exchange of photons. And then there's gravity. This equation represents Newton's law of universal gravitation. Let me walk you through this. F is for force, G, little baby g as a subscript, is the gravity. It's equal to big G, which is called the universal gravitational constant, and I've shown you the number there. It's just a number. And you take that number and you multiply it by mass of one thing times the mass of the other. Okay? And that first mass, think back to the parachutist. Mass 1 is the Earth. Mass 2 is the parachutist. And then we divide it by the distance between the middle of the Earth and the parachutist. That's R. We square it. We get a number. So this is Newton's law of universal gravitation. Anybody got an idea why it's called universal?
I'm going to say because it's a universal law.
It is a universal law, but there's two reasons why it's universal. One, it works everywhere in the universe, and two, every object in the universe attracts every other object. The current estimate of the size of the universe is 93 billion light years. That means if you're traveling at the speed of light, it would take you 93 billion years to get from one side of the Earth, one side of the universe to the other. An object on one side has a gravitational force on an object on the other side. That R, the distance between them, is really big, which means the gravitational force is really small, but it's still there. And so let's go look at where gravity comes from. There's two theories. The first, which I've already introduced you, is the idea of gravitons. Just like the gluon is the strong nuclear force, the photon is for the electromagnetic force, the W and Z bosons for the weak nuclear. There's the idea that there's this particle called the graviton. The trouble is we haven't found it yet. So there's this other theory called general relativity, courtesy of Mr. Einstein. He said that mass, anything that has mass, deforms both space and time, creating a quote-unquote hole that smaller masses fall into, which means in this case gravity is not a force. It's a displacement of space-time. And that'll mess with your head a little bit.